Geotechnical and Material Committee at the Society of Engineers, and as well as through the GGE, Geotechnical Gulf Engineer platform. We will have today in our speech Professor Ghanim Kashwani, Dr. Mark Balouz, Engineer Hamza, and for sure our keynote speaker, our main speaker, Professor Jie Han. So our first presentation, it will be by Professor Ghanim Kashwani, a UAE national, Professor of Civil Engineering Practice. He has his PhD from Heriot-Watt University, Scotland in UK. He is a Chartered Civil Engineer or Fellow Chartered Engineer, CEng, from the Institute of Civil Engineering. He's also a Fellow of the Energy Institute, EI, at UK, Chartered Environmental Engineer as well, and Chartered Manager. Hold his Bachelor and Master from the American University of Sharjah. He has also an MBA from the University of Wales, Trinity St. David's at UK. He's the former team leader in Abu Dhabi National Oil Company, ADNOC, and also he's taking the lead research in the higher technology college, higher college of technology in the United Arab Emirates, and as well as he's designated as an chartered scientist in the UK. So Professor Ghanim, you have the floor. You can start now your presentation about the Geotechnical and Material Committee in the Society of Engineers.
Thanks a lot, Dr. Marwan. Good evening, everybody here from UAE. First of all, I thank all the attendees here and all the people who organized here, Engineer Hamza for all his efforts. So if you allow me, if I can share my screen. Okay, and hopefully that my screen is clear. So first of all, this is Ghanim Kashwani. Welcome all to this session. And as you can see, we represent the Society of Engineers in UAE, and this is a committee, a new committee. We call it Geotechnical and Material Engineering Committee. So this committee have been newly established in 2023, and I'm happy to present the founding members. So I'm happy to present Dr. Marwan, the vice president, the founder member, and I usually say to him, he's the real founder and he's the real president. You know, he have been behind this since all the times. So Dr. Marwan, he's the founder member, and also my professor, Professor Dr. Jie Han, who taught me in the university. He's we call it the champion behind the curtain. So Professor Zahad, he also one of the founder member, and he's attending this presentation, and we send our regards to him. And as you can see that there was a lack of geotechnical committee here in the region. And today I have around 10 minutes to do my presentation, and today we talk about the importance of having these committees, especially in geotechnical, because in civil engineering we have a lot of structure, civil material, but to have a specific committee in geotechnical is very important, especially in our area in the Gulf, that we have many challenges like erosion, high humidity, subsidized. So today we'll talk about the importance of this committee under Society of Engineering umbrella. So as I said, it has been established in 2023 under the Society of Engineering. We have the official establishment and the letter from them, and we want to do in this group and committee, we want to focus between academia and industry, and this is exactly what we want to do. That most of us, we have an academic career and we have a lot of publication, yet we have people who are in the industry, you know, especially like Professor Zahad, Dr. Marwan. They do have a lot of experience in the industry and in academia. To shape this committee, we want to address all the challenge, not only in the UAE, our starting point definitely UAE, but also to go abroad and to communicate between industry and academia. Definitely geotechnical in general challenge, the innovation sector is, I call it blue ocean. There is a lot to do in it, and I was reading that one of the area that you need to improve in the water level rising is geotechnical, because many people, when we talk about global warming, we talk about the melting the ice, and then we have flooding. But one of the reason actually is the subside of the soil, and we need because we don't have a lot of innovation, the geotechnical and strengthening. So this is extremely important that geotechnical engineers, they play a critical role of saving lives, especially in these times with the global warming. And due to that, we need to have a sustainable practice. And we have a lack of codes, and I think Dr. Marwan, Professor, they can agree with me, and also Professor Jie Han, how it is important to have a critical sustainable practice that clear for the industry and updated by academia. And due to that, today we have this our session, and our target, as I said, is not only to have it locally, to go internationally, because we do need this collaboration in the worldwide. So locally to international level. And to do that, as you said, we need the collaboration between the industry and academia, and to have international guidelines. And to do that, we involve the word materials. I remember talking about the geotechnical, because there is a great relationship between these two, between geotechnical and materials. And if we cannot have the sustainable, durable materials, and let me say using smart materials. Many people, when we said smart materials in geotechnical, we are heading many areas. First of all, durable material environmental friendly, also material that can harvest energy. Especially these days, we need material that harvest energy. And there is a lot of research going on geothermal. And the fourth thing, we talk about self-sensing material that can give you data for the AI. Believe it or not, in construction industry and in civil engineering, 90% of the data are not utilized. We are just utilizing 10%. And this is one of the things we want to do within this committee, to use this updating things and AI that can help us to do algorithm prediction. And this is one of the targets we are targeting in this committee. Objective, as we said, establishing the platform between academia and industry, and drive the research, but that research should be industry oriented more, and to do that, we'll do a workshop and training. And we are lucky that in Society of Engineers, we have a facility that we are welcoming everybody, and it is almost free, and we want people to come and collaborate with us. So please, if you have any idea or research, please come to us. This committee is new, and we are looking for opportunity, and we have the infrastructure. In the last December, we had an event, and it was a great effort by Dr. Marwan, and it was our first establishment. And also now we have also international relation. We have our friend Dr. Mohammed Wahbi with GeoBear, and we are working with them also, and we have we have them in our event in Dubai. So although we are a couple of 3 months like in age of this committee, but yet we succeed to have international and relation, and we work on international event, and we are targeting more. These are the pictures that have been taken. I couldn't come that day, and I attended only virtually as here. Due to the distance, I'm in Abu Dhabi, and driving to Dubai sometimes is challenging for me. Now there is initiative that leading by Engineer Hamza, and we call it Gulf Geotechnical Engineers. And I think this will be the beginning point for it. This initiative that in the Gulf area, because we have almost the same challenge in terms of the geotechnical and the weather and the formation, and this initiative will help a lot. We have challenging of, as I said, erosion, earthquake, the water that we have it here, that we need the water security, how we can make sure that we don't lose the groundwater. So all these challenge, I think, will suit. It will be suitable to have this association. And as I said in the beginning, we have lack of international codes, we have lack of guidelines, and we have lack of committee of geotechnical engineers as a civil engineers. By this, I will end my presentation. And as I said, thanks a lot of attending this to whoever attending. And I'm very, I do mean optimistic about this committee that have been formed by Dr. Marwan and Professor Zahid. And I can see all the positive and outcomes hopefully is coming in the future. Thanks a lot, and I'll stop sharing my screen. And if you have any question, I'll be more than happy to take it.
Yeah. Thank you, Dr. Ghanim or Professor Ghanim. Really, to be honest, Dr. Ghanim or Professor Ghanim, he did a great job to get this committee approved under the Society of Engineers. For sure, we need a lot of geotechnical engineers in the region, especially in the United Arab Emirates, to be part of this committee. Professor Jie Han, as the chairman of the Geotechnical Institute in ASCE, for sure we need your experience and your support for the new committee, as well as from Dr. Mark Belluz as a SSNG as well, ISSNGE. And for sure we will be sharing the email and the contact details related to the committee, and we are expecting any effort or any support from the geotechnical engineer in the United Arab Emirates. So, Dr. Ghanim, really thank you so much, and now highly appreciated your support, and for sure we will be in touch. Now we apologize. I think Dr. Mark Belluz, he couldn't make it, so due to maybe some technical issues, but we will move to Engineer Hamza Al-Hashemi. So Engineer Hamza Al-Hashemi, his presentation will be basically related to the initiative was mentioned by Professor Ghanim regarding the GGE platform. Hamza Al-Hashemi, he's an MSc master. He has his master from the King Fahd University, as well as his civil engineering bachelor was from University of Khartoum. He's a PhD student now, and he's the regional manager of GeoFem in Middle East and Bahrain, as well as he's the CEO or the technical director in Geostructure. He has over 11 years experience, and he is one of the designers, or the designer of the largest micropile raft in the world, where he did it in Bahrain. He has he has experience in soil structure interaction, remote sensing, climate change, and advanced geotechnical methodologies. He's active in academia because he's also part-time teacher, part-time lecturer in University of Bahrain, and as I mentioned, he's a student now, or is a PhD student in IIT Bombay in India. So Hamza, you can start your presentation, you can share it, and you can start.
Thank you, Dr. Marwan, and sorry for the technical issues with Dr. Mark Belluz. He couldn't join, but he sends his regards, and he's looking forward to meet us in another event. Thank you for the introduction, Dr. Marwan, and I'm not sure if Dr. Zahid want to add something because he's with us now. Dr. Zahid, if you want to add anything.
If you open.
Thank you, Dr. Marwan. Thank you, Dr. Ghanim. Thank you, Hamza. Very nice to see you all in such a nice initiative, and congratulations to great work by Dr. Marwan to initiate that project, and great support from Dr. Ghanim too. He is our kind of what it says, the top person to support us Anyways, thank you
Yes.
very much, everyone. I'd really like to see all those nice people together. Please accept my regards in that, and I hope to work on many different initiatives together in future, inshallah.
Thank you.
Thank you.
Thank you.
Okay,
Thank you, Professor.
I need to say that Professor Zahid, I talk with him 4 courses, and he's one that teach us is not that impacting the society and giving back to society is all about to be engineer. So thank you, Professor, for that.
Great. Thank
pleasure.
you. Thank you, Professor. Thank you, Professor Zahid. Just for information, Professor Zahid is a professor in the American University of Sharjah, and as well as he's a specialist in geotechnical earthquake engineering. He has a lot of publications and a lot of research in that part of the soil dynamic and geotechnical earthquake engineering. So Hamza, you can start. Thank you.
Thank you, Dr. Marwan and Dr. Zahid as well. So as mentioned by Dr. Marwan and Professor Ghanim, this whole thing started as an idea among many passionate geotechnical professionals and geotechnical engineers in the Gulf region, and this was the spark behind Gulf Geotechnical Engineers, which is GGE platform, which was one of the small cornerstones behind the establishment of the Geotechnical and Materials Engineering Committee, GMEC, of the Society of Engineers in UAE, which I believe is the first geotechnical entity, official geotechnical entity in the whole Gulf, which is really promising because, as Professor Ghanim said earlier this evening, that most of the major projects and challenging projects geotechnically are taking part in Gulf. So this was the main motivation behind establishing this. We are a small community in the Gulf, so we want some umbrella to connect us all together and to organize events. I cannot claim the attributes alone. It is a result of many teamwork and individuals who supported us initially, each representing their respective regions. But if you want to attribute it, it was founded by Dr. Marwan Alzaylaie and my humble self as well. So the vision, we created this non-profit, I would say, organization or platform, Gulf Geotechnical Engineers, as a smart, sustainable and connected geotechnical community within the Gulf Corporation countries. We want to facilitate and exchange the knowledge among the geotechnical engineers and professionals within this region. And as the title of this event suggests, that for the Gulf and beyond. And it is evident today we have Professor Jie Han from United States, so it's actually a globalization. We want to serve as a hub for geotechnical engineering discussions, mindstorming, job opportunities and industry updates, keep updated with innovative technologies. Our values is to ensure professionalism in the platform, innovation, and encourage such innovation and innovative techniques and technologies. Unbiased approach, of course, as non-profit, we are unbiased to any of the entities or industrial parties. We want to foster collaboration with the global and regional chapters and entities like the Society of Engineers, the American Society, International Society of Soil Mechanics and Geotechnical Engineers, ICE, DFI, and many others locally and globally. And we want to continuously engage the community through the online discussion and informative sessions, which is why we are conducting such kind of events. One of our key achievements, we have exceeded, thank to all of you who made this possible, we have exceeded 1,000 followers on LinkedIn. We have established our own YouTube channel where all our events are published for free, recorded. We have successfully created GeoTalk, and if you remember GeoTalks, this what became now or evolved as GeoVirtual. And we have nice involvement throughout last year. We started with the first one with the Bechtel on Riyadh Metro project, and then we moved to a case study with Dr. Anil from Rock Science on foundation analysis, and then with Dr. Muhammad on geohazard chemistry perspective, and then the last GeoTalk was with the Bile Draft Foundation with Professor Harry Paulus. We have extensive registration for our events, exceeded 525 engineers, and this event, GeoVirtual, is no exception with Professor Jie Han as well. We also proud to be participated as the official platform partner in the IGIC, which is the International Geotechnical Innovation Conference in Jeddah, taking place on May 2024. We encourage everyone to be there to register in this event. We will make it remarkable. Many brilliant minds from all over the world are participating. Different partners, the ACI, ASCE, IGS, ISSMGE, Deltaras, Emerald Publishing. We have extensive outstanding technical committees and keynote speakers and speakers. Professor Jie Han today, of course, will be there, and hopefully we'll meet him in Jeddah. So if you are interested, please don't miss this opportunity to be with us. There are a lot of industrial sponsors, so it will be industrial based conference. So please don't miss this opportunity to be with us there. And feel free, if you are not already part from GGE, feel free to scan this code and it will take you to our page. Follow it and keep updated with our events and sessions and technical talks and GeoVirtual. And that's it. Over to you, Dr. Marwan. Thank you.
Thank you, Hamza. Really amazing initiative, and really thank you even for the Geotechnical and Material Committee in the Society of Engineers. And now we will move to our keynote, our star of this event, Professor Jie Han. I think everybody knows him very well. Professor Jie Han is Roy A. Roberts Distinguished Professor at the University of Kansas in the United States. He's the president of the ASCE Geo Institute. He's the chair of the U.S. Transportation Research Board, Transportation Earthworks Committee, treasurer of the International Geosynthetic Society. For sure, he's an expert in geosynthetics, ground improvement, pile foundation, buried structure around roadways, and also in a lot of different fields in geotechnical engineering. He earned his BS and master, his bachelor and master from Tsinghua University in Shanghai, China, and his PhD from Georgia Institute of Technology in the United States. For sure, he has an amazing and outstanding book, Principle and Practice of Ground Improvement, one of the important reference to design the ground improvement in the world. And he reviewed more than 450, he published more than 150 papers, and he delivered a lot of lectures. He got a lot of awards, such as 2014 the IGS Award, and 2017 ASCE Martin S. Kapp Foundation Engineering Award, as well as he got in 2018 ASCE Kansas University City Engineer of the Year Award. I think if I continue in this direction, will take a lot of time to present you Professor Jie Han. I'm sure everybody is waiting to your valuable information in ground improvement. So you can start, Professor, for your presentation. Thank you.
Thank you, Dr. Marwan, for your kind introduction, invitation to this event, and also congratulations on the establishment of your committee. And I also brought a message from Dr. Mark Bruce, and he couldn't log on the system, and he encouraged you to establish a national society and then join the International Society of Soil Mechanics and Foundation Engineering. From GI side, I'm looking forward to collaborate with you on different events like the conference that you organize. But today, I'd like to talk about the recent advance in ground improvement technologies with a focus on ridge inclusions. And as you know, there are many ground improvement technologies, and it is impossible to cover all in next 45 minutes. Then I pick up a few technology I found interesting, and there's new development, and I will share with you. And then I move on to talk about ridge inclusions that will be the focus of my presentation. But here's the outline of my presentation. Start with the introduction to show you the problem we face. And I think even though we are in the different countries, probably you will face similar problems. And then we'll talk about recent advance in ground improvement technologies. Then we'll talk about ridge inclusions. And at the end, a few concluding remarks. So this is a picture was taken actually in Malaysia. And as you see, there is a city here, but they are trying to expand the city to the coast. And they do land reclamation. And as you know, in the coast area, there's a very soft soil, what you see here. So how do we build the buildings, roads on this kind of soft soils? This is challenging, right? So we have to do something. The ground improvement come in can help very much. So that's what they are doing here. But also, even after we build something on the soil, you may see some problem like this. But this is the problem, basically the highway on the bridge, the basic approach to the bridge. So this is on the bridge side. Basically, most of the bridge foundations supported by pipe foundations. The embankment may be sitting on the soft soil. So as you can see, there's a very clear differential sediment. And this they use the approach slab. You can see here that when you drive the vehicle from this direction, you will feel basically jump or bump at the end of bridge. But if you cannot see clearly about differential sediment, then you can see the distorted guardrail that very clearly this side said much more than other side create this differential sediment. Now, this is a very small bridge in Australia. And I was invited to give a lecture, and then I had a little bit time to walk around, and I walked into the park and observed this small structure have very interesting phenomena, and I took a picture of this. But this is a bridge basically with people to work on it, and then maybe small vehicle to maintain the park. So there is no heavy vehicle at all. But here basically is like a bridge abutment and with a little bit deeper embankment, and you see there's no sediment, but approach embankment, this is the approach slab, and it's the soil underneath the saddle by itself create a void, and you see very big differential sediment and a very big bomb at the end of bridge. Even for very small a bridge like this, you may have problem like this. So basically, differential sediment is a common problem for geotechnical applications. But how do we avoid this kind of problem? The ground improvement can come in to help. So when we're dealing with buildings, those are the options for foundations. So if you're lucky, you have a good soil, firm soil near surface, so you may build the building on top on the soil with shallow foundation. Now, if the soil, the poor soil is not very thick, then you may be able to excavate the soil, replace with good soil. Then you build on that replaced soil. Now, for some situation, then you may apply some, if the soil is a little bit deeper, then you may apply the like dynamic compaction to densify the soil underneath the buildings, or you can use the pre-loading technology to press the soil first before you build the building. But those things you can do here. And next option, if the soil is very deep, and then you may install some kind of column. And then on top of that, typically you have a cushion. And the color, you can have a different type. That's what I will talk about today, include the rigid inclusion technology. Of course, you can use another approach, use a pile foundation. So you may use a very long pile, and basically everything counts. The pile will carry the load. That typically is the more expensive approach than other approach. Now, among this, but when we do over excavation replacement, you may even use the lightweight fill. If the soil is really soft, you want to reduce the pressure of the replacement soil, you can use the lightweight fill, and I will show you one picture later on. So all this is basically part of ground improvement technology. The one thing I want to share with you regarding the intelligent compaction, the Professor Kashwani mentioned earlier on, smart technology. So this is one of the smart technology. In the past, when we do the compaction, typically we count the number of passes, and after reach the number of passes, and then you go to do some kind of density test at the very few points, and to make sure that you achieve the density. But that technology it's not very good, because you really don't know how the soil has been compacted, and your density test at very few points where they will be representative to the whole site, because the soil is not uniform. Some places may be compact pretty well, some places may not compact very well. But now we have technology and install the sensor. But this is the accelerometers. They are installed on the compactor, and when the compactor move on the soil to generate some kind of vibration, and then from the vibration we were able to know what the soil responds, and then can see from the screen with different color code. So here I'll show you an example. This is a test site. They will divide into like 5 different lanes, and then do the compaction here. So as you see here, on the first pass, you see the red color means the soil is not very well compacted. Okay, and most area, as you see for the first pass, the color is red. The basically density is not good. Second pass, there's the 0 points with the red, and they continue until to 8 passes. As you can see, mostly turn into green. The green means the soil has been well compacted. So from this map, you very clearly see some more areas still not good, like here, and there's still the red point. So for that location, maybe some special soil there, maybe like organic soil there, and maybe that was over the river. You cannot compact soil very well. So for that case, you may go there to get the soil out, replace it with the soil, do compaction again. So that gives you a really big picture about the site, how the soil has been compacted. And for some time, you don't need to reach to 5, 6 passes, maybe 3 passes will be enough, maybe 4 passes will be enough. So that will give you, very good information, make a smart decision. So this is the one technology called intelligent compaction. The next one I want to talk with you regarding lightweight cellular concrete. And as you know, soil is heavy. When you build the embankment, you build high embankment that create very heavy soil load on the soft soil, especially if you have soft soil. Now we can use the lightweight aggregate, but the one I want to share with you is the lightweight cellular concrete. So basically, this composed of cementitious mortar with discontinuous random air bubbles formed or introduced through form. The basically 3 things: you have cement, you have foam, you have water mixed together and generate called lightweight cellular concrete. So if you look the density here I have two different units here, but look this side for metric units. As you see, the density is much lower than soil. For typical soil, if you know, typically like 1,800 to 2,000, right? But this about like 1/4 of the weight of the soil. However, their strength is high because this is kind of like a concrete material, okay? But that is the typical density used for most geotechnical applications. So here basically show you the picture, and we did a project to build the retaining wall with steel reinforcement. You can see those are the steel reinforcement, and on that side is the concrete facing, and basically you pump this cereal concrete just like slurry, okay? And the nice picture about this, I took by myself. As you see, the compactor just sitting there doing nothing, and for that technology, you don't need a compactor, and you just pump the slurry and fill the area for backfill. And then, that becomes solid, it becomes very strong, and then, you finish up the project. And this is the picture after reach the top of the retaining wall. Now you can see the facing here, and then basically finish up the construction. So it's a very fast construction without any compactors, and you can build the retaining wall very quickly. Next technology, I talk about vacuum preloading. So the side I show you early on, like land liquefaction. And the side I show you the mud, the very soft soil. Typically, you will not be able to have equipment get on top of soft soil, and you will not be able to place any backfill material because it's too soft. The one technology will work very well is the vacuum preloading. That basically you will place the membrane on top of soil. Now below that, typically you have the thin blanket or cushion, allow the water to come out. And those are the PVDs, the prefabricated vertical drains. Basically accelerate the consolidation. As you see by the animation, the water will travel from here, come here, and then go out by the pump. And this utilizes the air pressure, because after we apply the vacuum underneath the membrane, then you have atmospheric pressure. That's equivalent to like 100 kilopascal. Now, then you say, well, what if I need more than 100 kilopascal? That's no problem. Then you can put a surcharge on top of this. Then you can increase the pressure. But at least with the vacuum preloading, without surcharge, you already generate enough strength in the very soft soils. Then after that, you can place the surcharge, you continue to the vacuum preloading, then you continue to consolidate the soil. So here basically show you one picture of the real construction. So as you see here, this is the geomembrane, and on the top, this is basically surcharge material, and this is the pump here. So as you see the pump connect with this one. Now there's a couple little details here. As you see, this is the trench with the water. As you see here, the reason I have trench basically try to steer off the leakage at the edge of the geomembrane to prevent the leakage. Another little detail here, as you see that the soil layer on top or between the granite material and the geomembrane, there's like a sand layer there. The sand layer basically protect the geomembrane from damage during the construction, place the granite material, because granite material tend to punch through the geomembrane. So that layer basically protect that. Okay, now let's move on to talk about geosynthetics. And geosynthetics, there's many different types. As you know, geosynthetics are manufactured products, polymer materials. And I've been working on geosynthetics for many years, and especially for roadway application, retaining wall applications, and embankment applications. So here I show different types of geosynthetics. One is the non-woven geotextile. If you're not familiar with this is the woven geotextile. And this is a special woven geotextile. It's called weakened geotextile. And I also refer to this as a smart material. And Professor Kashwani mentioned early on smart material. Then I'll show you how smart this material is. And then GeoNet, the geocomposite used for drainage purpose. So I show you the 3 different type of geogrid here by Excel. This is the early version. was invented in 1980s, and then triaxial geogrid that was invented 20 years ago. This is a brand new product they manufactured released last year called multi-axial geogrid. Now, what's different here? This is a square shape, and this is a triangular shape. As the way you expect, the triangular shape is more stable than the square shape. Then this is unique geogrid. Basically, there's 3 different shapes, 3 different sides. As you can see, this is one here, and another triangular here. Okay. Now, why produce 3 different shapes, size? Because we know that for aggregate has gradation. That means the aggregate size different in the mass of soil. If we have a different shape, different size, the particle will interlock better with those apertures. All those products, basically the planar geosynthetic, there's one product called GeoCell, and sometimes also called GeoWeb. And this is basically 3-dimensional, as you see the pocket with some depth. There's a soil, stay inside is confined, right? So we have done a lot of research on the GeoCell stabilized roads, but because of time, I will not get into detail about this technology. But let me expand a little bit about the weakened geotextile, the smart geotextile. The light color of the fibers basically has some shape like this, okay? As you can see here, it's an irregular shape. Now, what is the purpose of this? Basically, increase the surface area. But if the material has a larger surface area in contact with the water, they will develop called surface tension or suction. But basically, when we place the weakened geotextile in between the subgrade, the base course, and when you have rainfall, the water will come down, will suck into geotextile, transfer to the side, either evaporate or go down, drop. And if there's groundwater table close to the road and also capillary rising may come and will stop by the weakened geotextile and take it to the side. Now, why I say this is smart material? Because the weakened geotextile will work only if the soil has too much moisture. After the geotextile removes the moisture to certain lower level, the weakened geotextile will stop working. And then if you have a rainfall and if you have a rising ground table, and the geotextile will come back to remove the moisture. So that is the smart way to handle the moisture. Now, there's some results, as you can see here, for one project after rainfall, the color becomes dark. And a few days later, with the weakened geotextile removal getting lighter, that shows the moisture content reduction. This is basically moisture content data. But this picture, as you see here, this is the location of weakened geotextile. So as you see, the water table somewhere here, and rising by capillary rising, and then stop by weakened geotextile. And on top of this, the soil is pretty dry. As you know, if the soil is dry, the soil is strong, the soil is stiff, and it can carry load. So that is the way how we improve the road with weakened geotextile. Okay. Now let's talk about column technologies. The traditional one, as you know, is called stone columns. This is basically a vibro flotation technology. To inject the water into the soil, make the soil into slowly, and then you backfill with the aggregate, push the slurry out, and then you use this probe to densify the stone from the stone column. Right? The stone is stronger than soil, of course, but stone column require the lateral confinement. If the soil is too soft without the lateral confinement, the stone column cannot carry too much load. So now we come out to another technology called vibro concrete columns. For this technology, inject the air into the soil, and on the side you see here, basically introduce the concrete rather than stone. So basically, after you make the hole and pump in the concrete, withdraw the probe, you form the vibro concrete column. Now this process take a little bit longer time to do because you need to make the hole, introduce the the concrete, and it is a little bit slow process. Now we have better technology called auger displacement column. So this is the auger, but the auger down into the ground, and also as you see the change cross section. So this basically kind of like provide the lateral displacement expansion, okay, and then also can make the soil move, but that can be good, sometimes can be bad. So I will talk about this later on. This is the popular technology to make rigid inclusions. But inside that hollow pipe, you will introduce the concrete or cement slowly from the center. So when auger going down, they withdraw and the basic pump the ground into the hole to make basically auger displacement column. There's a reason for displacement because we use this expansion section to displace the soil. So as you may have heard about the biostabilization, and actually in US there's a center for biomediated, bio-inspired geotechnics. They have been working on for several years now, trying to develop the biotechnology. The biotechnology basically there's different way to do it, and one way basically create some kind of bacteria and then generate some cementation. They bond together. Those are the like basically like a concrete. Introduce the bioagent and interact with soil and then bonding them together as like a concrete that you can use for different applications, for tunneling, for embankment stabilization, for roadway stabilization, for different things. So this is the one thing. Oh, sorry. But here basically use the cone, the cups and the limestone fine and then mix together and then place mixed with the soil, basically by cement stabilize the road. So this is the one special application in Singapore because this part they don't like to use the real cement, and they has to be more sustainable material. They come out the bio cement technology to stabilize this. Okay, but we talk about different options for foundation systems. But here basically show the comparison from the French guideline and said, we have a shallow foundation, and then we have a deep foundation, like a pipe foundation. And they call this one is called mixed foundation. Basically different from those two. For pipe foundation, all the load carried by pipe. Shallow foundation is, all the load carried by soil. For mixed foundation, basically the pipe, the soil will share the load. The pipe will carry load, the soil will carry the load. Okay. But a lot of time we call this the piled wrap. And the last one, basically that's what we now refer to rigid inclusions. What's the difference between those two? Actually, the one thing the same, pile and the soil carries the load. But because we have the cushion or load transfer platform, then we will transfer more load to the soil actually, and the pile will carry less load. Okay, and for that case, you can have the compatible deformation between pile and the soil, and they will also, I will talk about later on, also reduce the concentrated load on the rock foundation. Okay, but this is the one we typically call pile foundation. So this is the pile rock foundation. Now, regarding rigid inclusion, actually there's different terminology used in different countries. Now, in US, you used to call columns. In the US, in Asia, for composite ground. And there's actually another way to called unconnected pile rock foundation. Now, this still refers like a pile. So a lot of people don't like this because the reason to come out the rigid inclusion that we treat the whole area as ground improvement rather than deep foundation. Okay, so that is conceptually different between the pile foundation and the ground improvement. Ground improvement basically say rigid inclusion is part of the ground, and this is just the reinforced element, but it's not the structure element. Okay, but conceptually that is the case. But later on we will talk about under different situations, those rigid inclusion may be still need to carry tensile force, they will still need the maybe steel reinforcement. Okay, then we'll talk about that later on. The one important feature of rigid enclosure is that they are not connected with superstructure. Okay, they're often with the cushion, also called load transfer platform, or sometimes we call LTP for that layer. Okay, what is the definition of rigid enclosure? I don't think that there's a unified definition, but this is just my definition here. Rigid enclosures are defined as a vertical elements that are significantly stiffer than the surrounding soil. But their vertical stability is achieved without any lateral confinement of surrounding soil. But as I mentioned earlier on, for stone columns, in order for stone column to carry load, you have to rely on the lateral confinement. Okay, but stone column is not rigid enclosure, in my opinion. I know some literature refers stone column as rigid enclosure as well. A load transfer platform is installed between the top of rigid enclosures and bottom of superstructure or embankment. But we are working on the rigid enclosure now. We have one project, but we just did a survey about what type of element is considered rigid enclosure. But based on the survey the data, as you can see, that most people select drill displacement column, as I showed you earlier on. Okay. Then we also have one. The second one is the auger cast piles. Okay, and some people even think a timber pile is rigid enclosure. Okay, but different people have different opinions, and as long as this one is much stiffer than soil, and put into the soil with the cushion on top of this to carry load, that typically considered rigid enclosure systems. And regarding drill displacement columns, there's different tools available by different contract. The here basically show you different shape and different type, and the main idea basically drill down into ground, displace the soil, then backfill with ground cement, and to form the rigid columns or rigid enclosures. Okay, but basically there's two different type of systems. One basically used to support the embankment. They're also called like column supported embankments. But for this system, as you see, that you have the column or rigid enclosures, and you may have a geosynthetic, and that this is the layer called load transfer platform, and on top of this, basically embankment. Typically, we try to minimize the differential sediment between the rigid enclosure and refractive surface. So we need to make sure the critical height should be below the embankment height. Right? Second system basically use instead of use embankment, based on top of this, use the wrapped concrete wrap. But you still have a low transfer platform, but you have a wrap on top of this. For this case, most cases you don't use geosynthetic because of the wrap. You can bridge over between the rigid enclosures. And this is the results I gathered, and to show you the percentage of coverage. And here basically show you the definition. Column coverage, basically the column cross-section area divided by the unit stair area or inference area. Now, there's a different terminology you may see in the literature. Sometimes we call percent coverage, and the most common use is called air replacement ratio. Okay, the reason you use the percent coverage because sometimes you use the pie cap. If you just column, a lot of people call air replacement ratio, basically how much area the soil has been replaced by column. Okay, so if you look at actually back 1975, there was a paper published, and that provided guidelines for conventional pie supported embankment at that time called pie supported embankment, and that's a requirement for the percent coverage is 30 to 70%. Okay, then when I published a paper back in 2002, and I got survey the results from different projects around the world, and I draw the line here is about like 10 to 20%. Now, the reduction of the percent coverage or air replacement ratio basically means you use the larger spacing of the column and you basically reduce the cost. And recently, I collect more data, and the recent data show something around 5%. Okay, but that basically after people start to use the regional inclusions and continue to reduce percent of coverage or area preservation. Okay, of course that will create a more economical solution, but sometimes also create a problem because if you have a lower percent of coverage, you will provide less support for structure for embankment. Okay, but the French guideline show the percent coverage of area preservation 2 to 10%. That is kind of consistent to what I collected data recently. Okay. Now, in terms of applications, and the first most the application basically dealing with the core approach embankment, as I mentioned earlier on, the problem to dealing with differential sediment. The bridge is supported by piles. The embankment supported by pile or rigid enclosure now we call with geosynthetics, and basically try to transit sediment from almost zero to some little sediment. Also used for pavement support and also used for tank support. So this was the early application in the United States back in 1990s. They were used the fiber concrete column with the 3-layer biaxial geogrid to support the storage tank. So I did this project in Brazil, and we use basic jet grout column to support retaining wall with the LTP. So I did another project with roadway widening. So basically say if you have existing highway and on the subsoil, after you use like 20 years, and then you want to widen the highway, now you build a new portion, so you may face the differential sediment between the existing because the sediment has been complete, and you add a new material here, and also maybe adding the new material causes the sediment on existing embankment will cause the crack on the pavement. But we use the fiber concrete column and with geosynthetic to support the new embankment. So this is the interesting application, and I got a picture from Professor Zhou in China. After I made the presentation, he told me one application I never thought about this, and they use basically rigid inclusion with geosynthetic to support pipe. And he said that is the area for one project. They have the uncontrolled field, it's non-uniform. But they were worried about if you place the pipe in this direction or that direction, may have a crack or may got a damage of pipes. But they build basically install the column, pipe cap, in their platform, and build like a uniform foundation for those pipes. And that is an interesting application use the rigid inclusion. Okay, show you some picture here, and those two basically were project in Germany, and they were widening the railroads. So another side, the existing railroad, this new railroad. As you can see here, basically underneath that there's the pie or rigid inclusion, now we call, and then here basically pie cap. And the little detail, as you can see, at the corner, they cut the edge to make avoid the stress concentration, and then on top of this, place a geotextile or geogrid with this. But this was the one project in New Jersey, and approach embankment to bridge. So this used fiber concrete columns, and after they finished, they had some repair of some column head, and then place the geosynthetic. As you see here, basically this is the low tension platform above the fiber concrete column. Then on top of this will be embankment. Okay, so before I talk about some designs and some test results, I would like to start with the mechanics of composite mechanics, composite materials. Actually, the things we are talking about, composite ground, the thing we're talking about, rigid inclusion, actually in the mechanics, this basic part of a composite material. And now here basically you have 3 different situations. Now in the composite materials, we have the called metric, basically for us in the soil. And then they have fibers for us, basically rigid inclusion. Okay? So if this subject vertical load, So if this subject horizontal load, if this subject shear force, actually the equivalent modulus basically they are different. Okay, but the theory, and they call represented unit volume element. For us, we typically call unit cell. Okay, they're basically the same thing. But there was a theory was basically proposed, like 1889. Okay, called equal strength. Basically, say if you apply the vertical load, with equal strength, just like foundation, rigid foundation, and then the fiber and the metric will carry load, and eventually you can treat as equivalent modulus like this. Okay, so this is the equivalent modulus combined from the fiber, combined from the metric. Okay, basically combined from rigid inclusion, combined from soil, and this formula has been used very commonly in ground improvement. The VF, fiber volume fraction, basically the L replacement ratio. Okay, everybody use it, and work on pretty well. However, not too many people pay attention to lateral load, shear force. But there's another theory was proposed 1929 that equal stress condition. But the formula is look like that. It's not exactly like this one. Okay. But the modulus of this one, basically this L replacement ratio, this fiber modulus, this soil modulus, and then I will show you example how that affects the real number. Okay. Now, if we're dealing with shear, and the formula similar to this one, okay, look like this. Okay, but let's. This is called rule of mixture. Then let's take an example to help us to understand. But let's say if the rigid inclusion modulus is 100 megapascal, soil modulus is 1 megapascal, and the shear modulus is 2.5 times different from the elastic modulus, like 40. Okay, the soil is 0.4. So let's say the L replacement ratio is 0.1. Okay, as I mentioned, for the French guidelines, like 2% to 10%. That is basically 10%. Then what will be the results? The E1 will be equal to 10.9. But basically say that the equivalent modulus of the composite foundation over the soil is about 11 times. To be increased by 11 times. That's very effective, right? That's very effective. Now, if you dealing with the lateral stress, only increase by 10%. Okay, that is basically what you got. And if you're dealing with the shear modulus, also increase by 10%. Okay, but we really need to be careful when you're dealing with the composite ground. It was support the vertical load, very, very effective. But if you want to use to support lateral movement, okay, so you will not get much benefit because of the low percentage, even though the rigid growth is very stiff. Okay. Okay. Now let's talk more about the column modulus effect. As I mentioned, I published this paper in 2002, and did the numerical analysis, use the unit scale, and use the finite difference software, the FLAC, and build basically the column here, the subsoil, geosynthetic, embankment, and the surcharge. A lot of people cite this paper, and then here basically show you some basic properties, those kind of things. And what I want to show you here, basically there's two different kinds of sediment. One is called total sediment, basically on top of the rigid inclusion, but this is the maximum sediment I'm talking about here, the total sediment. Another thing is differential sediment. Basically, the sediment by the column itself, the sediment by soil, because soil sediment is more than column, then it generate differential sediment. But unreinforced means there's no geosynthetic, but there's one geosynthetic is red, okay? So I have a different modulus, intentional select, 3 different modulus region, and I will show you later on. But if you look at the one without geosynthetic, with geosynthetic for maximum sediment at the lower modulus, that's about 7% reduction. That is total sediment. Okay. Now, as you see, if you increase the increase the modulus, and actually the total sediment reduction will increase. Okay, they will increase to 19%. Okay, in other words, the rigid column will perform better or provide more benefit. Another thing, if you see here, that those are differential sediment. At the lower modules, column lower modules, actually the differential sediment reduction is less than the larger modules. Okay, but in other words, if you use like stone column, you will get 7% reduction of total sediment, but you also have a smaller differential sediment. Now, if you use deep soil mixing, that is the range you will get. And then if you go to the rigid columns, then basically you will get lower total sediment. However, you will have a more differential sediment between the column and the soil. But if you want to use the rigid inclusion, but really you need to use geosynthetic to minimize the differential sediment. Okay. But what column we consider rigid inclusions, and I basically suggest the column modules over the soil modules should be greater than 100 times. Okay. But basically the soil module is 1.6, is about somewhere here. Okay. But deep soil mixing, people ask, deep soil mixing is a rigid inclusion or not? And I would say depend on modules. If the deep mixing modules are low, maybe not a rigid inclusion, but deep mixing modules high, if you use more cement, you're close to a rigid inclusion. Okay. The benefits of geosynthetic are more significant when rigid columns are used. Okay, now let's talk about the two systems I mentioned earlier on. Rigid inclusion versus the pile raft. Okay, for pile raft, there's no cushion. For rigid inclusion, there's a cushion, there's an LTP. Now, how that changes the dynamics is quite a lot. As you can see here, let's assume the footing is rigid, okay? Basically, the pile sediment and the soil sediment at the top is equal, right? With the depth, as you see, let's say the pile, if the is rigid, everything is the same, but soil sediment will decrease with it. Okay. Now, if you look at the rigid inclusion with cushion, as you know, at the top of this, of course, sediment will be equal. However, between that, actually there is different way of the different sediment. So from here, there's a cushion compression above the pile. Okay, then the pile will penetration like uniform. So the soil start from top or deform like this. So you generally, as zone like this overlap, okay, and basically say the soil will deform more than pile, and the below one section, the pile will deform more than the soil. So that plane basically called neutral plane. Okay, and then if we look at the shear stress, for pile, as you know, there is a shear stress, something look like this. Okay, that's a typical distribution of the pile shear stress, and also you will have higher shear stress in the raft. Okay, now if we use the cushion, what we reduce the vertical load here. The shear stress in the raft will be smaller than this one, but because of the deformation, that is the negative skin friction happen on top of the pile, and below that there will be positive skin friction, and that is a new plan. But that portion sometimes we call down drag situation. But if we look at the active load, as you see here, because the pile directly into contact with the raft, you will have a higher concentrated load. So for that case, you require the raft to be steel reinforced. Otherwise, you may have, shear failure, the tension, bending failure, those kind of things. However, if you put the cushion there and the axial force with much less, there will be less concentration, and the axial force, will be lower. But depending on the situation, maybe you don't need a steel. But here, basically, axial load here, this portion will increase. Now look back here, the load on the top was higher and then decreased with depth. But this case, it's not, because the negative friction at the maximum tension in the pile is at the depth in the soil and then decrease. So all those things basically change the dynamic. The bacteria basically say if you use cushion, you will increase the segment. Use cushion will reduce capacity because you will have a negative skin friction. However, there's a benefit. Basically, use cushion will reduce the load concentration and then reduce the demand for the raft. Okay, so that is the benefit with cushion for rigid cushion. The pile raft foundation may be considered as a special condition of rigid cushion. Basically, the cushion thickness equal to 0. Right? Okay, there was study done in the past, and they actually look into this kind of difference. Now, at that time, people don't call rigid cushion. This is called unconnected pile raft system for the lower one. Okay, but here basically show you the different tests, and this is the result I will explain to you. The first one, just on the natural soil, but that is the R1, basically that the curve. If you add one pile, and of course you increase some capacity, add the 4 piles, you increase more capacity, add the 9 piles, increase more capacity. Okay, and then if you see how much load carried by soil, and as compared with total load, if you have 9 piles, and basically the soil carry less load. If you have only 1 pile, soil carry most load. Now, if you don't have a pile, the soil carry 100%, right? That makes sense. Okay, so how the cushion changes dynamic? If you put the cushion here, and for the one without the pile, actually will increase the capacity a little bit than this one. The cushion will increase the capacity. Now, at the same time, if it's 1 pile, actually they are very similar to this one. The cushion will change a little bit. However, if you talk about 9 piles, and or rigid cushion, if you prefer to call, you reduce the capacity as compared with this one, as you can see here. Okay, but that basically is the increase the segment. Now, if you look at the percent of load carried by soil, and for 9 the rigid cushion carry about like 60%. But this one, as you can see, carries 75% or more. Okay. Oh, I'm sorry, should compare with this one. So this will basically increase the more load transport to soil. This one is about like 20%, and this one carry like 60%. And then if 1 pile, as you can see here, this carry to 75%, this almost 100%. 4 piles, but this is only like 20%, this basically 75%. What that really means is basically after you place the cushion, more load will transfer to soil, soil will carry more load, and the rigid cushion carry less load. But in pile raft, pile carry most of the total load, while in rigid cushion, soil carry most of the total load. As a result, rigid cushion have a lower capacity in the large deformations. There are other research done in France, and this will also show the same result. Basically, this is the total load carried by rigid cushion divided by the total load applied. Okay, and from here, as you see, with the thickness change. Now, if the thickness equal to 0, basically that's pile raft, and basically the pile will carry 80%. Okay, but the rigid cushion carry 80%. But I'm sorry. But increase the thickness, as you can see, it will go down to 20% and go down to like 10%. So as the results show early on. Okay, so basically by placing cushion and transfer more load to the soil, and then we ask less support from rigid cushion. This is also the reason why you can space the rigid cushion at the largest spacing. That we talked about before, 2% to 10%, that is the percentage of rigid cushion, because that way you can utilize the rigid cushion more. Okay, regarding design, there's 2 things we need to consider. One, basically at the center of the embankment, another one at the edge. So the designs are very different. So within the center, typically we're dealing with the one only consider vertical load, But if at the edge, mostly dealing with the lateral, okay, and the stability issue. Now, in the past, we typically separate them. So basically design the load transfer platform by itself, and then design the rigid enclosure or column foundation by itself. But recent trends basically try to integrate them together. So I did some research and proposed the method, try to integrate the embankment design and the column foundation design together. I will show you some in next few slides. But before I go there, let me explain the load transfer mechanisms. And they're basically here, the column or rigid enclosure, and this is the topsoil. You have an embankment on the top. As you know, the rigid enclosure was settled less, the soil was settled more. Then you generate some kind of differential sediment. But if you look at this wedge here, basically we mobilize the shear stress. Then the shear stress will reduce the load applied on geosynthetics. If you have geosynthetics, but that reduces the stress, we typically refer to soil arching, right? But this is also the model proposed by Tazaki to explain the soil arching. Now, when the geosynthetic carries the load, and then we start to deform, and then we have the tension develop geosynthetic, the vertical component of tension will carry that load. That called tension membrane effect. So if we look at the column or rigid enclosure in the soil, as they interact, as we talked about earlier on, the soil deform more than the column, and that basically next to skin friction, there will be the down drag force induced at the interface. The column soil interaction is another thing is very important. But there are several parameters that we need to talk about. One is called soil arching ratio. Basically, the stress on top of geosynthetic divided by the overburden stress, or maybe even include surcharge. But that is to evaluate the degree of soil arching. Okay, if soil arching ratio is low, that means the soil arching is significant. Another way to evaluate is stress reduction ratio. But this is the one basically referred to under the geosynthetic. But that stress is reduced because of the soil arching and because of the tension membrane. But there's another terminology called stress concentration ratio. But this terminology is very common used in ground improvement, basically to describe how much stress concentrated on the column divided by the stress on the soil. Okay, but that basically tries to see how column really carries the load. But another parameter, as I mentioned earlier on, is called critical height. So this is what we call like an equal sediment plan. But basically above that, there will be no differential sediment. But we need to control the critical height lower than embankment height. Okay, but keep in mind of those terminology, and I will come back later on. But all depend on column to soil modulus ratio. But in terms of soil arching models, many different models available, proposed by different people. But I list all those here. Maybe not all, maybe I even missed some other people proposed the model. The first one, a representative one, basically called Tazaki model, basically vertical lip surface. Later on, there's adopted Tazaki, basically, this is the plane strain condition, and this is changed to three-dimensional, more used for column support embankment. Carson method basically assumes the soil arching is triangular. There's a group of people use that. So another one basically uses like an arch model. Here Randolph was the only one, and the British standard use that. The other people modified this. Basically, that's the one arch. Okay. In Germany, basically there's different height with different arch. More recently, but Dr. Van Ackering in Netherlands, she proposed the called concentric arch. Basically, that's a little arch in the middle, and then another arch, another arch. This is more appropriate for geosynthetic reinforced case. And then there was a study done by the PhD at the MIT, and he proposed a basic centrifugal test, and he observed some phenomena, and basically the arching ratio changed with the displacement. Okay, this trapdoor test to simulate the soil arching. The trapdoor test was developed by Tazaki. So basically say if there's a zero displacement, that soil action ratio will be equal to 1, so the stress on top of trapdoor will be equal to overburden stress. Now, if we're going down, the trapdoor, basically the stress will reduce top of the trapdoor, that will basically develop some kind of small arch. If you keep going, then you develop a circular arch. You keep it going, it may develop elliptical arch, or maybe triangular arch, as we showed earlier on. And then you keep going on, will develop a vertical arch. Okay? But that's pretty high over there. But we published a paper in 2029. Basically, that curve is complicated, and for practical use, we simplified this to 3 lines. But we also defined, based on some results, the point of the maximum arching or minimum arching ratio is 1.5 to 5% of the width of trapdoor, and this is about 10% of trapdoor. And that really corresponds to Tazaki's solution. And then this curve is called ground reaction curve. Okay. So let's take a look. Some people did evaluate different soil arching models and try to see what's going on. So this is the case dealing with stress of geosynthetics with certain height. But here shows all different methods, as I mentioned earlier on. But one method was missing, was the very accurate model, the percentage of soil arching, because her model was published after this study. So I added this one here. But you see here, there's a wide range of difference in terms of stress on soil predicted by different models. So even here, so if you look, this can be 10 times different with the models. Which one we should use? Why they have different predictions? Okay, but basically this because of the model, the soil arching at a different stage. As I mentioned, soil arching really changes with displacement. You can have a small arching, you have a circular arching, you have a triangular arching, you can have a vertical arching. Okay, so basically, I took this one, a very accurate arch, potential arch, and a double Tazaki arch as 2 control points and develop the model. Okay, but the main reason for the calculate difference is that the soil arching model will develop at a different arch stage. But that was the model I proposed, and when I gave the about kernel lecture, and basically I determined this is the use the concentric soil arching. This is use the Tazaki arching at the 10%. But this is normalized stress on top of geosynthetic. And then this is how much load comes from the embankment. And if we consider the geosynthetic load to carry the vertical stress, use the tension membrane. So I'll not get into the detail of the theory formula because of time. Basically, just show you the concept. So the geosynthetic will carry some load, and the soil underneath will carry some load. Okay, but if you add those two together, you get this line. Now, what is the solution? Basically, the intersection is the solution because the stress on top applied from the embankment and equalized by the tension membrane, equalized by the soil underneath. So you find the solution for that. Okay. Now let me move on to next matter regarding the failure mode of ridge inclusion under embankment loading. The one I should talk about is under vertical load, but under embankment, you may have sliding failure, you may have location failure, maybe the ridge inclusion even break, or maybe as Brooms mentioned, it's a combination of compression, tension, and even shear or bending, or those model together. But I did a study before, and back in 2005, to evaluate deep soil mixing. Okay, and I compare with the shear failure model, basically use the Bishop. They were basically said if we use the Bishop method to analyze the slope stability, even consider the Prof method, this is dealing with stone columns. And I found that, if the column strength is lower, actually they match pretty well because this is the shear failure. Now, but if the column strength starts to increase and the Bishop, the shear failure model overpredict, especially during the bending. And then if you keep increased strength, actually for numerical analysis, those are numerical analysis, the fact that it's almost no change because the location doesn't matter how strong, the column, but for shear failure, the factor is way overestimate. Okay, but it is a very dangerous to use the Bishop method, the shear failure method to predict ridge inclusion like this, because when the stress getting high, this will become more like a ridge inclusion, and this more not like the ridge inclusion like stone column kind of thing. But as I mentioned before, the deep mixing can be ridge inclusion, can not be ridge inclusion, depend on the strength and stiffness. The other study done in China, they did some central feature study. This is dealing with the concrete pile as a ridge inclusion embankment, and they observed the breakage of the columns during the failure. The break of the column gradually, basically one by one, and eventually the whole embankment failed. Now, GeoTalks did help, basically did not change the sequencing of column progressive failure, but increase the load capacity. Okay, but here basically show you the load. At this load, those column break, and then this one, this column break, and this all the column break. Those kind of things. Okay, there was one study done in US and did the collateral load behavior study. Have a footing loaded and then apply the lateral load and with 4 piles and with the cushion with different thickness. So they use 0.4 to 1.2 and the French guideline 0.4 to 0.8. They range a little bit more. But here basically show you the curve lateral load displacement. So increase the thickness, as you can see, increase the lateral capacity, increase the thickness of the cushion, and also increase the thickness of cushion, basically reduce the lateral displacement. Most importantly here, basically increase the cushion, reduce the bending moment on the rigid cushion. That will minimize the bending failure of rigid cushion. That is the benefit of cushion. But they did excavate the soil and try to observe the failures. For the low transit platform, 0.7 meter, all 4 columns failed. 1.2 meter, the 2 columns failed, the 2 columns not fails. And they also observed that the tensile failure and the compression failure. But really that indicates the bending failure. The one side is tensile failure, another side the basic compression failures. Okay, there was study done dealing with the seismic behavior, but actually it's very similar results. But this is kind of shaking table with ridge inclusion, without cushion, without cushion, with cushion. And as you can see here, without cushion, basically those are the dash line. As you see, the bending moment is higher, but with cushion, the bending moment is much reduced. So that is the benefit to use cushion for rigid cushions. Now let's talk about liquefaction mitigation. As I mentioned, for the auger displacement column displacement, the lateral displacement may densify surrounding soil, and especially for loose sand, those kind of things should be verified by testing between inclusions. However, one thing I will talk about, people try to give credit about the shear stress reduction. Now, suppose rigid inclusion can carry shear stress and reduce the stress on the soil. They will basically get reduce the shear stress ratio by a factor here, basically stress reduction factor. So that is the one here. But you see here, like a composite concept, as I talked about earlier on, but people didn't study, found out there is the one factor should be applied, and that factor basically called compatibility factor. Okay, what I mean compatibility factor? Basically, the soil and the rigid inclusion, whether they move together. Okay, so if they move together, that factor will be 1. But let's take a look here. If this is a real shear, the column and the shear was soil shear together, the factor will be 1. Okay. Now, in reality, if there's a rotation, the column rotate, and that factor will be equal to 0. Okay. Basically, the modulus ratio equals 100. As I mentioned, the rigid inclusion, the ratio will be 100. For that case, if this is 0, you can do the calculation, basically come to something like that. That since the air replacement ratio is only 2 to 10%, this is almost equal to 1. Almost equal to 1 means there's no reduction. Okay. The first guideline say for region quotient, allow for limited increase on the order of 5 to 10% in the fact safety relative liquefaction. Okay. So basically that's what you can get. This 5 to 10%. It's consistent with what we talk about here. Installation effect of region quotient. So here basically the study compared 3 different kind of augers. The one auger without expansion, this one. 2 augers with expansion. But during the installation, USD generate large lateral movement with expansion one, less lateral movement without expansion one. And also can generate ground heave, okay? But you see the ground heave may damage the existing pile, okay? Or region quotient, if you want to call it. But that is something to be careful. And when you use this expansion technique, with general lateral displacement, but at the same time with general lateral movement and also body movement, okay? So how do we evaluate that kind of system? So here, basically, what I would suggest first, if you really want to see whether there's any densification, then you can do SPT, CPT test in the center of the columns. And or you may do individual column tests and then individual composite ground tests. Or if you have money, you can do multiple column composite tests as what is here with the large pad underneath and the box with the soil. Of course, this is very costly. But at least what I would suggest you do single column test and a single column composite ground test. With that, I reach the concluding remark. The recent advance in ground improvement provides smart, more effective, and sustainable solutions. The concept of region quotient has been used in different countries. For example, composite ground, unconnected pie wrap, and a column supporting background, but become popular in recent years. So more people now use this called region quotient. The advancement of installation equipment method in the theory have promoted the use of region quotients. The region quotient has different elements in the composite ground, improve the global performance and increase bearing capacity, reduce sediment instead of piles in the pile foundations. The load transfer platform is important for distributed superstructure load to soil, minimize stress concentration on the superstructure, and minimize the lateral load and the bending moment on region quotient as I discussed. The soil arching tension membrane is just next used in the downdrag main load transfer mechanism in the system. The unified method is proposed to design this complex system. Region quotient may have a progressive bending failure across the slope of the embankment or subject to lateral loading. Therefore, steel reinforcement is required. Region quotient may mitigate soil liquefaction by soil densification, but the stiffening effect of individual column through the shear stress reduction is very limited. But different installation method may cause different level of disturbance to surrounding soil and maybe even the pre-installed columns. The performance evaluation is needed for surrounding soils, region quotient, and the composite ground. With that, I thank you very much. Any questions?
Thank you. Thank you, Professor Jie Han. Really very informative presentation. We learned a lot through this presentation. We have a lot of questions, and I will let Engineer Hamza to take care about the questions, but I will take one question, which is, so I want to discuss it, which you explained it already. The question from Ahmed Abdel Majid, as well as from VJ Boshan, related to the effect of liquefaction, which you already mentioned it, and how the rigid enclosure could mitigate the risk of liquefaction.
But as I mentioned, basically there are two major mechanisms. One is identification, one is the shear stress reduction. But if you have a low sand, potentially for liquefaction, the ridge encroaching installation can densify soil, you will get benefit. However, if you want to count the shear stress reduction, the benefit will be very minimal. Okay, and the reason one is because the percentage of ridge inclusion is small, and the second, ridge inclusion may not behave like shear, more may behave like a bending or rotation, but that will not provide much benefit to the shear stress reduction.
Yeah, and let us put it in this way, in case we should investigate between the rigid inclusion and do again the test and see how this soil will be improved. And my opinion is similar to, with the normal pile you do it. So in the normal pile, okay, it could do some improvement to the soil, but for sure will not mitigate the liquefaction in this case. Hamza, you can take care about the questions. We'll try our best to take all the questions in case the time is not helping us. All the other questions will be sent it to Professor Jie Han, and he will reply and send it back by email. So Hamza, you can take care about that.
Sure, thank you, Dr. Marwan, and thank you, Professor Jie Han. It was extensive and densified content over this short period. I'm sure everyone is keen to know more. And for everyone, if you don't know, Professor Jie Han has a famous reference book in ground improvement you can refer to. And also, as I mentioned, feel free to come to our conference in Jeddah. Professor Jie Han himself will be there and he will explain more on that. We will have also a workshop with Bentley and Rock Science. So hopefully you can learn more and get hands-on experience. Continuing with the question, hopefully we have about 10 to 15 minutes to answer it. Ahmed Al-Majid again is asking Professor Jie Han for the unloading behavior of soft clay. When we stop the vacuum system and remove the loading, will it follow the improved soil or unimproved soil? And what about the creep behavior in that case?
You talk about vacuum preloading?
Yeah.
Okay. For vacuum preloading, is different from the field preloading. Vacuum preloading, even though we have atmosphere pressure, but we're generally more like lateral movement or like equal confining condition. The vacuum preloading, typically you will not have a failure like field preloading. That is the benefit. But vacuum preloading also have a problem. When you apply the vacuum, you generally inward the soil movement maybe create a crack. And this is why you see all this. But I think what the question regarding unloading, after you finish the vacuum preloading, whether there will be rebound. Of course, if you unload, there will be a rebound. But as you know, the soil rebound deformation is much less than the loading stage, right? But you will have a rebound. And then if you want to place the structure on top of this, as long as your applied pressure less than pre-stress level, the deformation will be very small. But if you feed that pre-stress, meaning pre-loading load, the deformation started getting larger. But that is basically is like a compression consolidation curve, what you talk about like that. Yeah, you will get the rebound, but it will be small, and that's basically my answer here. Thank you.
Perfect. Thank you, Professor Jie Han. Another question I do have, what about factors like the lateral loads and tension loads and quality assurance and quality control when it comes to rigid inclusions? Are these challenges or limitations considered for rigid inclusions, or it can be overcome?
Yeah, regarding lateral load, this is still things for debate, and a lot of people think for rigid inclusion there's no need of steel reinforcement. because this is a part of the ground and the ground improvement. But if you have a stick element in the soil, if there's a differential movement, there will be bending. That this is the mechanics. Okay. Conceptually, people think this is everything the composite. You don't need to consider the tensile stress in the rigid inclusion. But the mechanics basically tell you, if there's different segment, if there's bending, there will be tensile stress. So for that case, you need the reinforcement. Okay. But I would not say for all the cases you need that, especially if you subject the vertical load, definitely you don't need this. But if the rigid inclusion subject the lateral load, if it's subjected, slope stability at the edge of the column, like bending, you need steel reinforcement for rigid inclusion. If you really want to rely on the bending resistance. Now, if your design ignore the bending resistance, of course, that will be okay.
So clear. Thank you, Professor. Another question about the stone columns from someone in KFUBM is asking, how can we increase the stability of compacted granular material and make them more stable against upward flow of water?
Okay, I see the question about stone columns, and I published a paper about the consolidation theory for stone columns. That basically, if you're dealing with the sediment, stone column has two major benefits. One is drainage. This is obvious if the stone column is kind of clean and high permeability, you can provide as a drainage path. Another benefit is called stress reduction, vertical stress reduction, because stone column will carry more load than soil. But if stone column carry more load, this means that there's a reduction to the soil. As you know, if the soil has stress release, the pore pressure will release as well. But there's two benefits there. In the theory I developed, basically consider both benefits. Okay, with that. Now, in terms of slope stability, we published a paper as well, and the stone column will provide resistance to increase the effectivity, because mostly due to the shear failure. As I mentioned, if the column subject to shear, you will get a benefit. If the column subject the bending or rotation, you will get a less benefit. Okay, but however, for some situation, the stone column benefit, you need to be careful, especially their original theory basically consider stress concentration on top of the column, but we find out at the failure, actually the stress concentration almost equal to 1. But you should not consider stress concentration at the failure. Now the stress concentration ratio actually exists under working load, okay, but not exists at the failure. But when you deal with slope stability, because we're dealing with failure, the stress concentration ratio should not be considered there. But you still get the benefit of the high friction angle of stone column.
Hamza said
it. Thank you.
One question from Bashir
sure.
Khan, you missed it, yeah. From Bashir Khan regarding rigid inclusion are with reinforcement or without. Yeah, exactly. Yeah.
Yes.
If you take the question, Hamza, yeah.
Yeah, sure. So this Bashir Khan, I'm not sure if you, Professor Jie Han, already answered this or not, but he's asking, do we usually design or use the rigid inclusion with reinforcement or without? And if yes, why? Because the rigid inclusion purpose is to improve the soil stiffness.
Yeah, I think I already answered this question, but I can say that again. Basically, what I said, if rigid inclusion are used to carry vertical load, you don't need the steel reinforcement. But if rigid inclusion need to subject the lateral load or bending, then you need the steel reinforcement. Basically, that is the answer there.
But just an addition, even the minimum reinforcement is not required in this case?
That is a good question now, because for some situation and observe the installation damage, but during the installation cause the soil movement, even the ground heave, that may cause damage to the region cushions. But if for that case, of course, the added steel reinforcement there will be helpful. But depending on the spacing, of course, what spacing you use, and also the installation sequence is very important. But you don't go one by one next to each other. But typically, you will move around and try not to create too much pour the pressure during the installation, because especially use the auger displacement method. When the soil displays generally pour the pressure, and then generally the lateral movement of the soil, right? Then you push the next ridge cushion. But if you change the order of installation, will minimize the soil movement, that may avoid that kind of problem.
Yeah, if you allow me small things, so we should follow the minimum reinforcement of the pile of the or the minimum reinforcement of the cross-section concrete, because there is a big difference between both. Yeah, yeah.
I don't think we have done enough research on this. Maybe this is the topic of research. Yeah, but we don't want to go back to the pile foundations. I mean, that is the whole idea. People come out of the terminological ridge inclusion. If you go back all the way to pile foundation, and that would be different, because we're really dealing with the ground improvement, not the pile. Yeah.
Yeah. Thank
you. Thank you, Professor Jie Han. I think we have a question or a comment from Astrid. She said the mechanics of composite material springs in parallel and springs in series. I'm not sure if you have a comment or answer for that, Professor Jie Han.
I don't know the question. What is the question? That's not question, right? It's a comment over.
Astrid is with us, I believe. Yeah, Astrid, I can unmute you and you can ask if you want. You can unmute yourself and speak.
Hello. Good afternoon, all.
We hear you.
Actually, good evening. No, it was just an observation because of the equation used for the determination of, say, the equivalent modulus when you work with inclusion, whether you look at compression or shear or lateral. So that equation reminded me a lot about springs in parallel and in series. It was just an observation.
Yes, that's exactly right. One is in series, one is parallel. Exactly.
And it's a beautiful analogy.
Yeah, exactly. This is why, because a lot of people use the parallel stereo, basically get the higher equivalent modulus, and but in reality, for different loading conditions, they are different. And a lot of people treat it as the same. That's what I demonstrated early on. The modulus increase by 11 times, but really you only get the 10% increase if you subject to other type of load. Okay. But this is something I think theoretically, fundamentally, we need to understand that. Don't apply that theory to everywhere, because under different loading conditions, different.
Thank you. It was a beautiful, yeah. Thank you.
Thank you.
Thank you, Professor Jie Han. Another question from my colleague, Tamnoy Das from IIT Bombay. He's asking, between stone columns and PVD, which method should be chosen for liquefaction or mitigation? Mitigation. This is the first question. The second one, for stone columns, how we determine the required depth for each project?
Okay. Between the PVD and the stone columns, and to mitigate the liquefaction, PVD basically just provides the drainage path. That's it. Stone column can densify the soil during the installation, and also have a shear stress reduction benefit, and also can serve as drainage. But stone color would be better than PVD if just for that comparison. Of course, PVD is much cheaper than stone color, right? And but that is something you need to consider. In terms of the benefit, the stone color carries more benefit than PVDs, because PVD is flexible. There's no stiffness. You install the PVD, you will not densify the soil. I mean, because it's so small. But those benefits PVD will not have. Second question regarding the depths, right? In terms of depth, it depends on different applications. You know, if for the sediment calculation, of course, there will be a depth there, and you based on the bearing capacity and also based on the inference depth, you do some calculation like that. For the liquefaction purpose, and that's also the depth as well. And there's some code that provide you the depth say below certain depth, then you don't need the volume of liquefaction because the overburn stress is high enough and those kind of things. But I would suggest not to go below that depth, otherwise there's no need for any kind of degradation or stress relief.
Perfect. Thank you, Professor Jie Han. Another question from KFUPM. They are asking about the residual load in piles, how it affects the stability of the ground. Is it important to take it into consideration during the ground improvement process?
Residual load pile? I don't know what that means.
Residual loads in the piles.
Residual loads on the pile. I try to understand
this. I could unmute you, but I'm not sure who is this guest. Okay, we'll skip.
Maybe you could move.
So please feel free. Feel free to reach to us. Maybe we can direct your question to Professor Jie Han. Another guest is referring to your reference book, Principles and Practices of Ground Improvement, and he wished if there is a new version of that, so maybe you can share the good news, Professor Jie Han, on that.
Yeah. Actually, I'm working on the second edition. The schedule to be published next year, I've been really busy. I don't know whether I can finish it all, but I tried to finish this year and hopefully I can publish it next year. But I will update that book with new information, and some of you probably find some typo error here or there. We'll try to correct those. That's my hope to publish the new edition of this book next year.
So we are all looking forward to it, Professor Jie Han. Another question from Reem. She's asking how to deal with the limited strength of rigid inclusions, which you have mentioned in your conclusion. Would we use two methods together to solve this? Can we use a combination of methods?
I did not hear the first part. The limit of what?
The limited strength of the rigid inclusions. Yeah.
Limit the strength.
Rigid inclusions, which you have mentioned in your conclusion. I'm not sure if you mentioned such thing in your conclusion, limited strength of rigid inclusions.
Actually, I have not published, and I did come up some way to consider the column benefit in the slope stability. But I just need to find the time to publish all the stuff I have developed. There is a way to consider rigid element in the soil to increase the fact safety of the slope stability, use the limit equilibrium analysis. And I don't know whether that is the things was asked. There is a way to do that. I think maybe related to something what I mentioned, do not use the Bishop method to do the analysis for the stability if involved in rigid element. I think the reason, because I said a Bishop method or any limit equilibrium method assume soil, column, fail, and the shear. But in reality, when the column getting stiffer, very likely not basically have a shear failure, instead have a bending failure or have a rotation failure. But that is something, as I mentioned, I came out with a method to basically consider this kind of effect because of bending or rotation. But I have not published that paper yet, and hopefully I will publish it in the near future.
Awesome. Another, I think, 2 or last 3 questions. First one from Mohammed Abdul Wadoud. He's asking, what is the effect of vibroflotation or vibration stone columns on the mixed soil? I see value ranging between 2.4 to 2.7 between the columns. Do we expect much improvement of strength and stiffness between the columns?
Okay, that's a good question. I mean, it depends on soil type, of course. But if this is a pure clay, you will not get any benefit. Then if this is a loose sand, you will get a benefit, right? The number you talk about basically depend on soil types. 1.1, 1.2, 1.3, and also depend on spacing as well. You know, if you have a closer spacing, then you will get the more benefit, especially for loose soils. But I don't know the exact number for different type of soils, but this definitely can be evaluated in the field testing or SPT, CPT test. Typically, the conservative way to test at the central of the columns. Of course, if you want to do more careful testing, you can do on the column and then between. Some people have done something like that for sand compaction piles, and they did the test on the sand compaction piles and between soils.
Thank you, Professor. Another question from Ahmed Awad. He's asking, do you accept or recommend isolated footings on improved ground using stone columns?
What footing?
Isolated footings on stone columns. Yeah. Do you accept it or recommend it?
Yeah. People use that all the time.
Another question from Bashir Khan. What kind of test usually recommended for rigid inclusions, like load test is required on rigid inclusions or not?
Yeah, and as I mentioned, I think close to the end of my presentation, if you want to evaluate the improvement of the soil between rigid inclusion, I mean, you can do SPT, CPT test. And if you want to evaluate rigid inclusion itself, but I would suggest you would do individual rigid inclusion test, but at the least single rigid inclusion composite test. What that means, composite test means that the load plate will cover the rigid inclusion and the soil. Just like a unit cell, you need to have the size of loading plate same as the unit cell to be represented. Now, if you have more money, then you can test like 9 rigid inclusion altogether. That requires a lot of load, and of course it will be more accurate. But at the least, that's my suggestion, to test single rigid inclusion composite, okay, that include the soil with cushion, okay, that you get some number there.
Actually, if you allow me to add, Professor, usually some of the projects here, we go for the zone load test to check the whole system, how it works related to the rigid inclusion. Plus, I'm not sure if we should do a specific single test for the single rigid inclusion, but as a zone load test to confirm if the bearing capacity is achieved after we do it after. Yeah.
Dr. Marwan, zone load test. What is zone load test? Like you have the loading plate large enough to have a.
Yeah, exactly. Say foundation of 2 by 2 or 3 by 3, and we take a certain and we do it in this way. Yeah.
Okay, yeah, that's what I'm saying. If you have a budget, of course, that would be the best. But if you don't have a budget, then that one stay single one is the kind of minimum you will do. Yeah.
Yeah. Okay.
Thank you, Professor. Thank you, Dr. Marwan. I think Mahmoud Al-Sakkar is asking, is the lectures being recorded? Yes, it is recorded, and Professor Jie Han agreed to provide also a copy of the slides, and there will be certificates as well. We will communicate it to you later on. Another last question, I believe, from Ahmed Awad. How about the durability of rigid inclusions without reinforcement? Are they considered durable?
I mean, durability would be the same as a concrete, and how durable for concrete in the ground that would be same as this one. But I don't think anything to do with the steel reinforcement. Steel reinforcement basically relate to whether there's a tensile force, whether there's a bending or not, right? But that is the thing. In terms of material durability, but just how durable the material will be, and I don't see any problem for concrete in the ground. Now, I did see some concrete in the coast area, exposed concrete that may have a durability problem. But if in the ground, I have not seen anybody concerned about the durability of concrete.
Just a small question: if it's required to do some integrity test for the concrete, similar to what we do in the pile, any standardization regarding to the minimum testing of the rigid enclosures as well?
I don't think there's any standard for that. Yeah, you're talking about integrity test. Yeah, people do that. Integrity test, just make sure there's no crack and those kind of things. Yeah, that is another good way to evaluate rigid cushions. Yes.
Okay, I think Hamza. If we
can just take one question. I think
okay.
Ahmed, one or two. One or two maximum. Ahmed Awad is back to the isolated footings question on stone columns. He said they have done testing in between the columns, but they found out the soil is not improved. So do you recommend anything in such cases?
Yeah, as I mentioned, but this is referred to soil. It's not a composite, right? For soil, if the soil is clay, you will not get improvement. That has nothing to do with the isolated footing or the mat foundation, same thing. But if you talk about the composite, you should get an improvement. If there's no improvement, that's a problem with installation or whatever. And but that has nothing to do with stone column technology itself. These are two different things. If you just measure the soil between the column, if it is clay, you will not get improvement. Okay, because clay will not be densified during the short time period. Clay only can be densified or compressed under sustain the loading like a preloading. If you have the load for a long time, let the portal pressure dissipate, then compress. If just during the installation, you will not get benefit of the soil.
Last question from Dr. Mubashir. He said, is dynamic response of rigid inclusions better than pile draft?
As I showed one results on the slide, yes, the cushion basically reduce the bending moment on the rigid cushion. If you connect the footing with the pile, like a pile wrap, during the shaking, there will generate a lot of bending moment on the pile. But if you have a cushion, then basically this is a more flexible system. The bending moment on the rigid cushion will be much less, as I show on one of the slides. But people did the shaking table test and basically demonstrate that. And there are other studies as well. Because of time, I cannot show all the research done by myself, those kind of things. Just a very quick go through. Because I did not cover the overall ground improvement technology, then rigid inclusion, try to finish within 45 1 hour time. Just not enough time to cover everything.
If you allow me, Hamza, I think
Sure.
we want, that's a lot. It's too much. We don't want to put a lot of. We don't want to do a lot of.
The closing remarks with you, Dr. Marwan.
No problem. Or with you as well.
Dr. Marwan, actually, this is very good. I have not seen so many questions for one single lecture like this. I like it, really. Thank you very much. All the people ask questions.
Yeah, actually, if you allow all this question, for sure, I think we'll finish in 4 hours or 5 hours. I think we already 2.5 hours, and thank you, really, Professor, for your informative presentation. I think one special request from regarding the new edition of the book to include more numerical modeling and example related to the rigid enclosure in new edition of your book. This is one of the good things, and I think you can be in contact with Hamza regarding. I saw a lot of questions related to the workshop which will be in Jeddah. You can ask Hamza and or the organizers. Professor Jie Han for sure will be in the workshop as well. He will be a keynote speaker in Jeddah conference. Thank you, really all. Thank you, Professor Jie Han. Really, we enjoyed today's lecture with you, and it really was really informative information. Personally, I asked some questions was related to some discussion of the projects, which will have it even tomorrow discussion and day after, and the future. So in the future discussions. Also, I would like to ask Hamza. Really, thank you so much for your presentation. Professor Ghanim Kashwani as well. I would like to thank you so much for your presentation. Professor Zahid Khan also for your explanation regarding the Geotechnical and Material Committee in the Society of Engineers. Thank you all the attendees for attending the conference and GeoVirtual, and we'll see you in future GeoVirtual series soon. Thank you, and thank you all.
Thank you, everybody.
Thank you, Prof.
Okay, bye.